Whoa! Nice pass, Bear.
Nice shoot too. Seems like you are good at football.
Well, absolutely. Actually, I'm also interested in volleyball, basketball, and table tennis.
Looks like all kinds of ball game.
Yes, these balls in my eyes are the most beautiful geometries in the world.
Really?
Sure. Well, actually, they are called spheres. Spheres are perfectly symmetrical.
Whoa.
They are smooth and graceful. Lots of things in our daily life I found to be
Cool.
like spheres, including our planet. Actually, there are numerous magic characteristics that we can find on the spheres. If you are curious
Whoa.
about them, let's today enjoy the fun on the sphere.
Perfect.
Hello everyone, I am Jimmy, a student from Working High School of Chongqing, China. Today, we are going to explore the fun on the sphere together. As we all know, our planet, the Earth, is also a sphere. Now, a magician really had a problem on the Earth and he really needs our help. He had a magic rope that went all along the Earth at the equator. Then he cut the rope and added 10 meters to its length. Then he let the resulting rope float above the Earth at a uniform height on the equator. Here comes the question. What is that height and how does the result generalize? Welcome back to the class. Did you get the same results as what we had predicted? As for me, my predicted value is much smaller than the real one because at the first time I think 10 meters was too small to have a significant effect on the length. Anyway, I will show you how my friend and I stimulate the process by using the sculpture behind us. Okay, first, we have used the rope to tie around the sculpture and now we'll get a circle. Let's measure the radius. Look how long the radius is.
Well, it is 0.64 meters.
Okay, now we have another rope 1 meter longer than this one. Let's go and measure that circle. This red rope is 1 meter longer than the blue one. Okay, now let's measure the radius. What is the radius?
Well, it's 0.795 meters.
Okay, now we can see that the difference between the radius of two circles is 0.159, which means that if we use a circle 10 meters instead of 1 meter longer than that one, the difference could be 1.59 meters. Is this result the same as yours? If you said yes, do you understand why our results are the same even if we used different sized balls? Okay, now let's get back to the class and do some calculations. Pay attention everyone. Now let's do some calculations on the blackboard. We assume that small r represents the radius in the previous and big R represents the radius afterward. According to the circumference formula we learned at school, the previous circumference is 2 pi small r, and when we added 10 meters to its length, the new length becomes 2 pi small r at 10. And this new circumference can be also expressed as 2 pi big R. Now we get a equation, 2 pi small r at 10 equals to 2 pi big R. After some more steps, we get big R equals to small r at 5 out of pi. And this value, 5 out of pi, is approximately 1.59 meters. This equation means that big R is always 5 out of pi longer than the small r, no matter how long the small r is. Obviously, from the equation, we can conclude that the result value will not vary as the radius of the circle changes, no matter the radius is as big as the Earth or as tiny as the small ball. Anyway, the result is truly counterintuitive because such a small amount of value can lead to such an unimaginable outcome. Not enough? Here I had a more interesting question. Muslim prayer is a physical, mental, spiritual act of worship. In this ritual, prayers have several steps to perform. Step 1, he starts standing straight on a rock, and this rock must face to Mecca, the holy city in the religion of Islam. Step 2, they will make their intention known in their heart by whispering something. Step 3. They will raise up their hand up to the shoulder and place the right hand over the left, focusing on the rock and reciting certain phrases. Muslim prayer who lives in Boston needs his rock face towards Mecca, flowing a shortest path. Mecca is east and slightly south of Boston. Now, here's a question. In which direction should the rock be aimed, and why? Welcome back. You eventually find the correct solution, right? In Boston, the prayer rock must be facing to northeast. Okay, now let's check the direction using a rubber band. Since the rubber band is elastic, right, it must follow a shortest path. Now, let's fix two ends at Boston, here, and Mecca, here. Okay, now look. Obviously, the direction is northeast. Quite surprising, right? Yet another counterintuitive answer. We are indeed having fun on the sphere. In fact, the direction that the rubber band flows is a minor arc of a great circle. By the way, a great circle is a circle on the surface of the Earth whose center and radius are those of the Earth itself. It is called great because the disk cut through the area is always the greatest. The circumference of a great circle is the circumference of the Earth itself as well. Now, let's imagine a perfectly spherical orange. We take a string and place it tightly on the surface of the orange. As the string cannot be put any tighter or shorter, it actually follows a shortest path between 2 points, which is prescribed by a minor arc on a great circle. It is the minor arc because, as you can see, the green line is always shorter than the red one. If you are curious about this and wondering why it is the shortest way, try to prove the theory after class. After we understand the concept of spherical distance, we can use this tool to solve some other interesting questions, like this one. There is a large community of stonefish, one of the most toxic aquatic organisms in the world, living in the Pacific tropic area. Recently, a marine biology research team in San Francisco is going on an expedition to the equator, the main habitat of these stonefish, to catch some specimens. As soon as they get enough samples, they will head to a laboratory research center in Shanghai to test those stonefish. Here's the question. Since the stonefish is widely distributed at anywhere on the equator, the commander should decide which is the shortest way from San Francisco to the equator and then to Shanghai they should go to economize the traveling expenses. In other words, which is the exact point on the equator that meets this purpose. We'll come back to fun on the sphere. Did you figure out a way to help the team? Now, let me show you how I did this with my computer. The trip starts in San Francisco, goes to the equator, and then to Shanghai. These three places are labeled with A, B, and C respectively. Okay, as we all know, the Earth is equally divided by the equator, right? So we can easily find a symmetrical point, A dot of A, on the south hemisphere. Okay, now look. The first travel segment is the same from our real orange north of the equator and from our reflective point south of the equator. So, wherever we visit the equator, the two segments have equal length, right? Look, as I show here, they are always equal. And the second segment to Shanghai is the same segment, whether we start north or south. So, we can reduce the problem to minimizing the sum distance from the reflected point to Shanghai, since this will also minimize the sum distance from the north point to Shanghai. Right? Remember, we have solved the same problem with the Muslim prayer problem, invoking the Great Circle idea. See, here on the screen, the red line is part of the Great Circle. So, when we move the equator intersection point to the Great Circle, like this, look. Notice here, the sum distance of AB at BC. The value is always decreasing when we move this point to the Great Circle, right? And when we move east or west of the point, the total distance starts to increase again. So, point D, the intersection point on the equator, is the point we should travel to. Though this trip seems like a two-step trip, first go to the equator and then to Shanghai. But when we figure out the symmetrical point, this trip truly becomes a one-step trip. This transformation method is widely used in mathematical world. The next challenge also requires another type of transformation method. Let's take a look at it. Hamilton was a famous Irish mathematician. In 1859, he analyzed a famous question. A traveler was planning for a worldwide trip. He chose 20 cities on the Earth as his destinations, which are located evenly in a lattice structure with equal distances between them. Each city has 3 airlines connected to 3 nearby cities. Here's the question: how to design a traveling route so that he can start and return back to his origin cities after visit all other cities once and only once. Welcome back again. Is it easy for you to figure out the route? Did you get back to the starting point? Are your results the same as Hamilton's solutions? I bet it's the same, but let's check. He turned the Earth into a dodecahedron. All of you did the same thing, right? Like this one. And the second step is the most intriguing step. He turned a 3-dimensional model into a 2-dimensional pattern. How so? Imagine we can twist and flatten this model. Now, here, we get a 2-dimensional pattern, like this one. With me so far? Okay, then for the third step, we can draw an appropriate road on this paper easily. Look, if we started here, and we go all the way like this. We go all the way like this, down here. Now, we are turning back to the starting point. Okay, then for the last step, we can rebuild this pattern into a 3-dimensional model. That is all. As you can see, in Hamilton's solution, we had 2 major transformations. First, we turned the Earth into a dodecahedron. And second, we turned the dodecahedron into a 2-dimensional pattern. We simplify the question, and it's much easier for us to cope with it. More generally, there are computer algorithms for solving such problems. Those problems are called traveling salesman problems. As you might be curious about this solution, a computer program for solving Hamilton's puzzle is available on the Blossom's download website. Okay, right now I bet all of you feel a little tired, right? So just stand up and let's go outside and do some exercise. Now follow my instructions and listen carefully. First, please remember where you are in present. Okay, second, now let's take 10 steps to the south. Let's count together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Stop and rest. Okay, now let's take another 10 steps to the east. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Stop and rest. Okay, the last step. Let's take 10 steps again to the north. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, stop. Please check. Did you get back to the starting point? Of course not. Yes, I heard someone said impossible. However, this trip is truly possible on the sphere. How so? Please listen to our last challenge. Okay, a person starts a hike somewhere on the earth. He first goes 10 kilometers to the south, stop and rest. Then goes 10 kilometers to the east, stop and rest. At last, he goes 10 kilometers to the north, and he surprisingly found himself back to the starting point. Okay, here's the question. How to identify all the points on the earth that could be the starting point for such a hike? Welcome back. Did you all finish? Did you all figure out all the points? Okay, I believe that your teacher have helped for the most difficult part, the points that near the South Pole. In thinking about how your class went, I believe that most of you have identified the North Pole really quickly, right? But when you hear your teacher say there are some other points, actually an infinite number of points, that caused a great deal of concerns, right? I remember when I first confronted with this problem, I did think of the South Pole, but I stopped when I realized it's impossible to go south from the South Pole because the South Pole is as south as you can get. Okay, eventually, with your teacher and with your classmates, you most likely identify the secrets. A circumferential traversal around the Earth, very near the South Pole. And the hike can start at any point 10 kilometers north of this circle. Okay? Actually, there are some other circles too, some other smaller circle. Each this circle has a paired east-west circle that's exactly 10 kilometers north of this smaller circle. And the hike actually can start at anywhere, at any point of this paired circle. This is because when we go east, we can make exactly 1 round, or 2 rounds, or 3 rounds of this smaller circle and return to a point where 10 kilometers below the starting point. Okay, at the last step, when we go 10 kilometers north, we can return exactly to the starting point. Wow, what a brand teaser! Well, as you can see, even though we cannot imagine such a trip on a flat plane, it is truly possible on a sphere. In fact, this is a specialty of the sphere. Well, I suppose when all of you are feeling surprised about the challenges or questions we discussed today, you must be feeling about the fun on the sphere. I have some suggestions for the additional explorations for you. Well, actually, there are numerous unknowns waiting for you to discover. For instance, the sphere triangle on a sphere has some really special and different properties. Well, besides, the parallel theory on the sphere is quite different from that on the plane. Oh, actually, as long as you are curious about these characteristics, you can enjoy the fun on the sphere. That's all. Thank you. The overall design of this lesson, from simple to complex, gradually stimulates students' interest. Displaying the fun on the sphere as some counterintuitive phenomenon will let students explore the joy by the process of hypothesis, confirmation, and summary. If you want to use this video to teach students, here are some friendly notions. First, before the class starts, the in-class teacher should lead students to form a group because teamwork is needed throughout the lesson. Second, a globe should be presented to the class throughout the whole lesson, for it helps students to visualize all the questions. Third, pay attention to the transition of each segment. They are interconnected. Fourth, mathematical thinking methods are also worthy to address. Fifth, when the activity involves dangerous tools like scissors, ask students to be cautious about them. Sixth, when they appear to be stuck and no further progress is visible, give students appropriate hints, making the puzzle less difficult nor too simple. Seventh, the proof for the spherical distance and program for Hamilton's puzzle are available on the resources download area on Blossom's website. Here are some guidance for each segment respectively. Segment 1. First, to help students solve this problem, the in-class teacher should prepare some materials in advance, which I've listed below. Second, before students use these materials, please ask them to write down a predicted value on the paper intuitively and mark it. Third, depending on the size of the small ball, they can change that 10 meters into 10 centimeters. Fourth, after students work out a reliable value, let them compare the result and the predicted value and see if there is a difference and figure out what caused the difference. Fourth, at last, ask them to think about these questions. Would the value change if the size of the ball become larger? Segment 2. A flat world map and a globe should be presented at the same time. Make sure that students know the location of Boston and Mecca on the map as well as on the globe. We are all confident that the shortest distance between 2 points on the plane is a straight line. However, when it comes to the sphere, a globe, is the appropriate direction the same? Third, then take votes from the class first. Let students select a direction intuitively before any work is done. Third, present a globe and a rope for each group to find a way and a soft ruler if needed to measure the distance. Tell students to minimize the distance as possible as they could. Fourth, at an appropriate time, give students an elastic rubber band if needed to help them find a correct direction. Segment 3. First, actually, this question also asks for the shortest way between 2 points. The only difference is that the team should travel to the equator in addition. The materials used in the previous segment, the globe, ropes, rubber bands, scissors, should still be available. Third, more importantly, use teamwork to solve the problem. Segment 4. Prepare a ball with 20 red line dots marked along it. Ask students to use their crayons or markers to match or highlight the route. 2. When the in-class teacher notices that students have matched the points and form a dodecahedron, he or she should provide a plastic model structure of dodecahedron to students and let them know that the model is flexible enough to change shape if they want it. Segment 5. First, since these segments involve some exercises, make sure the area is spatial enough so that no one gets hurt. Second, besides, when no more progress is made, give students some hints. For example, the points are infinite, or some points are near the South Pole but not at the South Pole.